Greetings, static students. I'm Parnian Gassemi, and today we're going to talk about structural analysis of simple trusses. Here is the overview of what we're going to go through today. The objective of this chapter is to become familiar with a simple truss. So what is a simple truss? And then to find out how to determine the forces in the members of a truss. And there are two different methods for this. The first method that we're going to cover today is the method of joints, and the second one is the method of sections. And here are the page numbers that you should study at home from chapter 6 of your textbook. All right, let's see what is a truss. Well, a truss is a structure composed of slender members joined at their endpoints. Well, in constructions, these members can be wooden struts or metal bars, but the thing that you should know is that they lie in a single plane. I'm pretty sure you all have seen several trusses in the roof of the buildings or in the bridges, so you all are familiar with the concept. Let's take a look at this figure A. Well, this truss is an example of a typical roof supporting truss. In this figure, the roof load is transmitted to the truss at the joints by a series of purlins. One of the most important things that I want to emphasize on is that since the loading acts in the same plane as the truss, you can see in this figure, the analysis of the forces developed in the truss members will be two-dimensional. We'll see that in some examples later. So as we just mentioned, trusses are used in bridges. Here is a very interesting bridge in Tokyo, Japan. And in the case of a bridge, the load on the deck transmitted to the stringers and then to the floor beams, and through that, eventually it will transmit to the joints of the two supporting side trusses. And again, the bridge truss loading is a coplanar problem, okay? So when a bridge or roof structure extends over a large distance, a rocker or roller is commonly used for supporting the end. So if you take a look at joint A in this figure, this type of support allows freedom for expansion or contraction of the member due to a change in temperature or application of loads. All right, let's jump into the design. Well, to design both the members and the connections of a truss, it is necessary first to determine the force developed in each member when the truss is subjected to a given loading. Well, to do this, we will make two very important assumptions. The first one is that all loadings are applied at the joints. Well, in most of our situations, such as bridges and those roof supports, the roof trusses, this assumption is true. Well, because the weight of the members is neglected. It's because the force supported by each of these members is usually way larger than the weight, so we neglect the weight. However, if the weight is to be included in the analysis, what do we do? We usually consider that weight as a vertical force divided into half and apply each half of that magnitude at each end of the member. All right. And the second assumption is that the members are joined together by smooth pins. Well, the joint connections are usually formed by bolting or welding the ends of the members to a common plate called a gusset plate, here in figure A, or by simply passing a large bolt or pin through each of the members. You can see it in figure B. Well, we can assume those connections act as pins, provided the center lines of the joining members are concurrent. Well, because of these two assumptions, each truss member will act as a two-force member, and therefore the force acting at each of the member will be directed along the axis of the member. If the force tends to elongate the member, it's a tensile force. We show it with a capital T. And if it tends to shorten the member, it is a compressive force, shown by capital C. Well, in design of a truss, it is important to know whether the nature of a force is tensile or compressive. Well, because usually compression members made a little bit thicker than tension members because of the buckling or column effect. That you'll know about it in future structural courses. Okay, let's know more about a simple truss. What is a simple truss? If three members are pin connected at their ends, they form a triangular truss that will be rigid, as you can see it in figure 6.5. Well, if we attach two more members and connect them at a new joint called D, it forms a larger truss that you can see it in figure 6.6. Well, this procedure can be repeated as many times as we want to form even larger trusses. Well, if a truss can be constructed by expanding the basic triangular truss, it is called a simple truss. Okay, so now we know what is a simple truss. Let's see how can we analyze and design a truss. Well, to analyze or design a truss, it is necessary to determine the force in each of its members. Well, one way to do it is the method of joints. Well, this method is based on the fact that the entire truss is in equilibrium. So, each of its joints should be in equilibrium, right? So, if the three-body diagram of each joint is drawn, the force equilibrium equation can then be solved to obtain the member force that is acting on each joint. Well, since the members of a truss are straight two-force members that are in a single plane, each joint is subjected to a force system that is coplanar and concurrent. As a result, we are supposed to check these two equations and make sure that they're satisfied for equilibrium. Sum of the forces in x direction equal to 0, and sum of the forces in y direction equals to 0. All right, let's take a look at an example together. Well, consider this truss, and consider the pin at joint B of this truss. Can you name 3 forces act on this pin? Pause this video, think about it. All right. As we can see, there is a 500 Newton force applied here, and then we have these two members connected at joint B. So we have members BA and BC. If we draw the free body diagram of this joint B, here we see there is a 500 Newton force here, and then we have the F sub BA and F sub BC. I know you're thinking, how did I know that this member is in tension and this member is in compression? Well, let's get back to the truss. This force is pulling on the joint in right direction, right? The member BA should be pulling should be in tension, right? And the right member, the member BC, should be in compression because of this force. Pause this video and make sure that makes sense to you. Okay, so F sub BA is pulling on the pin, which means that member BA is in tension, and F sub BC is pushing on the pin, and consequently, member BC is in compression. Well, we can see these effects by isolating the joint with small segments of the members connected to the joint in figure C. The pushing or pulling on these small segments indicates the effect of the member being either in compression or in tension. So, as I just mentioned, this force is pulling on the pin, so the right member should be in compression, should be compressed, and the left member should be in tension, because this force is trying to elongate the member. All right? Okay. Very important note is that when we're going to use the method of joints, we should always start at a joint having at least one known force and at most two unknown forces. So in this class, obviously, we're going to start at joint B. And then we can satisfy these two equilibrium equations in x and y direction. By solving these two, we'll have two algebraic equations which can be solved for the two unknowns when applying these equations. Well, one important way to find out the sense of each member is that when applying these equations, the correct sense of an unknown member force can be determined using one of two possible methods. All right. The first one is that the correct sense of direction of an unknown member force can in many cases be determined by inspection. So the first method is inspection. For example, F sub BC in figure B, in this figure, must push on the pin since its horizontal component F sub BC times sine of 45 degrees must balance this 500 Newton force. So we have this force in right direction. To have balance, the x component of F sub BC should be in left direction. That's pretty easy, right? Likewise, for F sub BA, it should be a tensile force since it balances the vertical component of F sub BC, which is F sub BC times cosine of 45. So this one's upward. The F sub BA should be downward to have balance, to be able to satisfy this equilibrium equation. Okay, so two very important notes. Number one, in more complicated cases, when we can't do the inspection very easy, the sense of an unknown member force can be assumed. Then after applying the equilibrium equation, the assumed sense can be verified from the numerical results. A positive answer means that the sense that we assumed is correct, and a negative answer indicates that the sense that we assumed on the free body diagram is not correct and must be reversed. So if we assumed it's in tension, it should be in compression, and vice versa. And note number two, always assume the unknown member force acting on the joint's free body diagram to be in tension, or the forces pull on the pin. If this is done, the numerical solution of the equilibrium equation will yield positive scalars for members in tension and negative scalars for members in compression, so we won't be confused, all right? And then once the unknown member force is found, use its correct magnitude and sense in terms of tension or compression on the joint free body diagram, so you won't be confused in your further calculation for the rest of the joints. Okay, let's review the procedure for this analysis, and then we'll have an example together. First step in analyzing our truss using the method of joints. First step is always draw the free body diagram of a joint having at least one known force and at most two unknown forces. Well, what if this joint is at one of the supports? Then what do we do? Well, in these cases, it may be necessary first to calculate the external reactions at the support and then go through the joints. Step number 2. Use one of the two methods described earlier for establishing the sense of an unknown force. What was those two methods? Inspection and assumption in more complicated cases. Step number 3. Orient the x and y axis such that the forces on the free body diagram can be easily resolved into their x and y components, and then apply the two force equilibrium equations, sum of F in x equal to 0 and sum of F in y direction equal to 0, and solve for the two unknown member forces, and then verify the correct sense. And step number 4, using the calculated results, continue to analyze each of the other joints. Remember that, okay, I'm not going to say that. Let's see if you're ready for a quiz. Oops, something is going wrong. Oh, here it is. So question number 1 says, when analyzing a truss, a member in compression, blank, on the joint. A, pulls, B, pushes, C, it could be both based on the applied load, D, it does not pull or push. And question number 2, when analyzing a truss, a member in tension, blank, on the joint. Again, pulls, pushes, it could be both, it does not pull or push. You have 30 seconds to work on this quiz. Okay, time's up. A member in compression pushes on the joint. Hopefully you got the same answer as me. And a member in tension pulls on the joint. If you didn't get the correct answer, you should go back and try again. Okay, now let's get back to our example, which is example 6.2 of your textbook. Well, we have this truss. It's asking for the forces in each member of the truss and indicate whether the members are in tension or compression. I want you to think about it and pause the video, think about it, and then we'll solve it together. Okay. Do you remember we said we should always start at a joint that have no more than two unknowns and at least one known force? So here is the joint that we should start at, joint B. And here is the x and y axis. By drawing the free body diagram of joint B, we have a 500 Newton force in this direction, and then we have F sub BA and F sub BC. So again, this is this force is pulling the joint B in right direction. So we can use either of the two methods of finding the sense of the member. But this member the BA member should be in tension, so it's pulling on the joint. And member BC should be in compression, so it's pushing at the joint. Well, you can start with assumption too. Okay, it's not a big deal. But if we see the components of F sub BC, considering this 500 Newton force in right direction, the x component of the F sub BC force should be in left direction to have balance, right? And the same thing for the y component. With writing the equilibrium equation in x direction, we have a positive 500 Newton force minus F sub BC times sine of 45 degree, which is the x component of F sub BC force, equal to 0. And solving this equation for F sub BC, here is the amount of the force, or the member force. And since we got a positive number, our first assumption of the member being in compression is correct. Either you assume or your inspection was correct. No need to change anything, okay? And by solving the equilibrium equation in y direction, here is our the y component of F sub BC times cosine of 45 degree minus, because this is downward, the F sub BA, minus F sub BA equals to 0. And solving this equation for F sub BA happens to be 500 Newton. And again, the results that we got is positive, so our inspection or our assumption was correct. It's in tension. Always check that. Always. Okay. Since we calculated the force in that member, now we can go to joint C. Here is a free body diagram of joint C. So it has a reaction from the support here, Cy, the F sub Ca, and a compression. We just got it from the past step, right? The compression force of 707.1 Newton. So with writing down the equilibrium equation in x direction, we have a negative force of F sub Ca, so minus F sub Ca, plus the x direction of F sub BC, which is 707.1 times cosine of 45 equals to 0. With solving this equation for F sub Ca, it will happen to be 500 Newton. And again, the sign is positive, so our assumption of the sense is true. So member Ca is in tension, okay? And we'll solve the equilibrium equation in a y direction for joint C. We have a reaction support Cy, and the y component of F sub Cb, which is 707.1 times sine of 45 degree, equals to 0. The C sub y happens to be 500 Newton. All right, our last joint, joint A. It has two reaction supports since it's a pin. It has A sub y and A sub x, and then F sub BA and F sub CA. So we have the amount and the sense of F sub BA and F sub CA. It's pretty easy to get A sub x and A sub y. They both are 500 Newton. Here is a summary of our analysis. Well, take a look at this picture. The free body diagram of each joint or pin shows the effect of all the connected members and external forces applied to that joint. whereas the free body diagram of each member shows only the effects of the end joints on the member. Okay. Next example is example 6.3 from your textbook. It's asking us to determine the forces in each member of this truss and indicate whether the members are in tension or in compression. I want to ask you to pause the video right now and try to solve it on your own. We'll get back and solve it together. Okay. Do you remember we always were saying that start with a joint that has at least one known force and at most two unknown forces? Okay, so can you see any joints having these conditions in this truss? No. So in this case, we should analyze the support reactions first and then go through the joints. And the reason is that easily there is no joint that satisfy that condition of having less than or two or less than two unknowns. Okay, so remember, we're always starting at a joint with at least one known force and at most two unknown forces. None of the joints in this truss has that condition. Okay, so for this example, I want to ask you to consider the whole truss as a rigid body. Okay, we have a vertical force applied at joint B and a horizontal force applied at joint D, and we have one reaction support here and for joint A, for support A, and two for C. I want to write down the equilibrium equation in x direction for the whole truss. Okay. Doing that, I have a positive 600 Newton and a negative C sub x. Obviously, the reason that I selected this direction is that this C sub x should have balance with the 600 Newton force, right? To satisfy the equilibrium equation in x direction. So C sub x equals to 600 Newton. Okay. Now, if I use the equilibrium equation in y direction, does that help me? Let's see. What do I know? I know I have a 400 Newton force in y direction. What else? I have an unknown force, a sub y, and another unknown, c sub y. So I have one equation with two unknowns. That doesn't help me. So what if I try to write the equilibrium equation for moment about point C? That may help because it will eliminate one of the unknowns, which is c sub y, because it applied at the center of the moment, right? So, okay, let's solve this equation. I'm going to try to solve moments about point C. Using your right hand rule, I have a clockwise moment that a sub y is making. So minus a sub y times 6 meter plus, again, use your right hand rule. I have a 400 Newton force that's making me a counterclockwise moment, so it's positive. So 400 Newton times 3 meter plus a 600 force, again, use your right hand rule. It's giving me a counterclockwise, so it's positive. Plus 600 Newton times 4, that's 4 meter, equals to 0. Solving this equation for a sub y, it happens to be 600 Newton. All right, now I can use the equilibrium equation in y direction, okay? I have a 600 Newton, which is a sub y, a negative or minus 400 Newton force, and minus c sub y. So this is downward. Solving this equation for c sub y, it happens to be 200 Newton. All right, now we can start at either joints A or C. If you're asking why we're not starting at joint B or D, well, that's easy because it still has a lot of unknowns. But since we have the reaction supports for joints A and C, the only unknowns that we have are these two members, the force members, okay? All right, starting from joint A. Here is the free body diagram of joint A. Here is their reaction support and the F sub BA and F sub F sub AB and F sub AD. Again, if you're not comfortable with the sense that we selected here, you can use the assumption method and do the calculation, do the math. At the end, if the results is positive, then your assumption for the sense, I mean compression, member being compression or tension, is correct. Otherwise, you should do it reversely, okay? By solving the equilibrium equation in y direction for joint A, I have a positive 600 Newton force and the y component of F sub AB. Solving this equation for F sub AB, it happens to be 750 Newton. And since my assumption was, or I used my inspection, for F sub AB, I assume that it is in compression. So compression members push on the joint. All right. So F sub AB is in compression. All right. I'm going to try the equilibrium equation in x direction for the same joint. All right. What do we have? We have a positive F sub AD and a negative x component of F sub AB. Solving this equation for F sub AD, it happens to be for 50 Newton. And again, since the number that I got is positive, my first assumption of the member being in tension is true. Now so I'm done with joint A. I'm gonna go through joint D. Here is the free body diagram of joint D. Let's see, what do we have? We have a 600 Newton force, the external force applied at joint D. I have the F sub AD or F sub DA force that I calculate in joint A, and it is 450 Newton. And then what else do we have? I have a F sub DC force and F sub DB force. So these two are unknowns and these two are knowns. Okay. By inspection, I can find the sense of this member, but let's do the assumption method, okay? Let's assume that F sub dB is pushing on the joint, okay? So it's compression. So let's assume it's a compression member. It's a compression member. By writing down the equilibrium equation in x direction, we have a minus 450 Newton and a positive x component of F sub dB plus a positive 600 Newton force equal to 0. Solving the equation for F sub dB, it happens to be minus or negative 250 Newton. All right, so what do we get here? We got a negative result, which means our initial assumption of the sense of the member was not correct. So we should reverse it. So the negative sign indicates that F sub dB acts in the opposite sense to that shown in this free body diagram. So F sub dB has a magnitude of 250 Newton, but the sense is tension. Okay. Now let's write down the equilibrium equation in y direction for the same joint. We have two options here. All right. To determine the F sub DC, we can either correct the sense of the F sub dB that we got here, and then apply the equilibrium equation in y direction, or we can apply the equation and retain that negative sign and substitute that into the equation and solve it for f sub dc. I'm going to do that. I'm going to retain this negative sign. Let's see what's going to happen. Okay, we have in y direction, we have a downward force, which is f sub dc. So we have a minus or negative f sub dc minus the y component of f sub db. So here is the magnitude I'm substituting in the equation, minus or negative 250 Newton. And then f sub dc, so with solving the equation for f sub dc, it happens to be 200 Newton. And look, I got a positive number. So my initial assumption of f sub dc was correct. So that member is in compression. All right. So let's go to joint C. Here is the free body diagram of joint C. We have CY and CX, 200 Newton and 600 Newton respectively. And what else do we have? We have a F sub CB, horizontal force, and a vertical F sub CD. Well, we've found out the F sub CD in previous step here. F sub CD or DC is compression force, and the magnitude is 200. So 200 and compression, and it's a compression or compressive force. So by solving the equilibrium equation in x direction, F sub CB, so we have a positive F sub CB minus 600 Newton is the reaction. F sub CB happens to be 600 Newton and it's positive, so our initial assumption of being the member being in compression is correct. And the equilibrium equation in y direction, what do we have here? We have a 200 Newton upward and 200 Newton downward. So this equation is just a check to make sure our calculation is correct. So 200 minus 200 is 0. Everything is in equilibrium. We're good. And here is a summary of our analysis. All right. Now let's know a little bit about the zero force members. It's obvious from the name that they're supporting no loading. So truss analysis using the method of joints is very, very simple if we can first identify those members that do not carry any load. These zero force members are used to increase the stability of the truss. So if you ask why we're using a member that is not supporting any load, well, they can increase the stability of the truss during construction, and they can also provide extra support if the loading is changed. The zero force members of a truss can generally be found by inspection of each of those joints. For example, consider this truss. And in this truss, consider joint A. If we draw a free body diagram of joint A, what do we have? We have F sub AF and F sub AF in Y direction and F sub AB in X direction. With writing down the equilibrium equations in both directions, we find out that F sub AF is equal to 0 and F sub AB is equal to 0. So we found out that these two members are zero force members. But let me ask a question. Can we do such analysis for joints, let's say F or B? Pause this video, think about it, and resume. Okay, we cannot. We cannot do such analysis for joints F or B because there are 5 unknowns at each of these joints. So we can't just simply write down the equilibrium equations and say here that the member is a zero force member. So no, we can't. How about joint D? Well, let's consider joint D. again, if we draw the free body diagram of this joint with this axis, what do we have? We have a F sub DE in X direction, and we have a F sub DC. Let's start with equilibrium equation in X direction. Well, how about starting the equilibrium equation in Y direction? The Y direction, what do we have there? F sub dc times sine of theta is equal to 0. Well, theta is not 0, so this term is not 0. Therefore, this term should be 0. So F sub dc should be 0. And if we consider the equilibrium equation in X direction, what do we have there? We have F sub dE and the X component of F sub dc, which is 0, so its X component should be 0. So F sub dE should be 0 to be able to satisfy the equilibrium equation in X direction. So we're able to simplify our calculations because we eliminate the zero force members for our calculation, and we simplified the truss. All right, so we can come to this conclusion that based on our observation, if only two members of a truss joint and no external load or support reaction is applied to a joint, the two members must be zero force members. Now let's consider this truss. Out of this truss, let's take a look at joint D. All right. If we draw the free body diagram of joint D, what do we have? We have F sub DE in this direction, F sub DC in this direction, and F sub DA in this direction. So we assume this is X direction and this is Y. Oops, sorry. With solving the equilibrium equation in X direction, we find out that F sub dA is 0 because these two forces don't have any components in this direction. And by solving the equilibrium equation in Y direction, the F sub dE and F sub dC happens to be equal. Now let's take a look at joint C. By drawing the free body diagram of joint C, we have F sub CD, F sub CB, and F sub CA. And here is the axis that we considered for joint C. Here is X and here is Y, the same as joint D. All right, with writing down the equilibrium equation in X direction, what do we have? We have, so these two forces, they don't have any components in X direction. So by projecting the F sub CA on X direction, its X component will be F sub CA times sine of theta equals to 0. Well, sine of theta is not 0 because theta is not 0, right? So this term, or F sub CA, should be 0. All right, so F sub CA is 0. By writing the equilibrium equation in Y direction, F sub CA and F sub CD will be equal. So we were able to eliminate these two members and simplify our calculations to a much simpler truss. Okay, so now we're going to come to this conclusion. Conclusion number 2, according to our observation, if three members from a truss joint for which two of the members are collinear, well, the third member is a zero force member. All right, let's see what did we learn and how can we use it in solving this problem. I want you guys to pause this video and think about using the method of joints to finding all of the zero force members of this truss. When you're done, please resume. Okay, so we should look for a joint that has 3 members, 2 of them are collinear. We can say easily the first member is a 0 member force. So this is the joint G, right? That has this situation. If we draw the free body diagram of joint G, what do we have? We have F sub GH, F sub GF, and F sub GC. Writing down the equilibrium equation in y direction will give us that the F sub GC is equal to 0. What else? Okay, so by eliminating this member, it's good to know that the 5 kilonewton force, the external force, is supported by these 4 members, CB, CH, CF, and CD. All right, how about joint D? Does this joint have the same condition? Yes, it does. It has 2 collinear members. The third one is with no external joint or reaction support, so the third member should be a 0 force member. We'll double check that. By drawing the free body diagram of joint D, we have F sub DC, F sub DE, and F sub DF. By writing down with X being in this direction and Y being in this direction, with writing down the equilibrium equation in X direction, these 2 forces, they don't have any components in this direction, so F sub DF, is equal to 0. All right, I want you to take a look at joint F now. Well, the F sub DF is a 0 force member. Now, what do you see in joint F? It has 3 members, 2 of them are collinear, and there is no external force or reaction support or anything, so the third member should be 0. Double check that with drawing the free body diagram of joint F. We have a 0 force, F sub FC, and then we have F sub FG and F sub FE. Considering X is in this direction and Y is in this direction, by writing down the equilibrium equation in Y direction, what do we have? We have the Y component of F sub FC equals to 0, which is F sub FC times cosine of theta equals to 0. Well, cosine of theta won't be 0 because theta is not 90 degrees, so this term, or F sub FC, should be 0. Okay. So far, we were able to eliminate these three members, that they're 0 force members. Let's take a look at joint B. All right, here is a free body diagram of joint B with 2 kilonewton external force. We have a force here, F sub BA, F sub BC, and F sub BH. Considering X axis in this direction and y-axis in this direction, and write down the equilibrium equation in x-axis. What do we have? We have a 2 kilonewton positive force and a minus F sub BH equal to 0. So F sub BH happens to be 2 kilonewton. So this member obviously is not a 0 force member. Could we do that without calculations? Yes, we have this 3 members connected at the joint B, but we have a external force there. So this member will not be a 0 force member, right? Now let's take a look at joint H. So by drawing the free body diagram of joint H, we have the F sub HA, F sub HG, F sub HC, and a 2 kilonewton force of F sub BH. If we write down the equilibrium equation in y direction, in this direction, the y-axis, we'll see that F sub HC won't be 0 because this one is not 0. So we were able to determine all of the 0 force members of the truss. Before we wrap up this session, I want you guys to do one last practice. I want you to write down the 3 new things that you learned during this session. If you don't remember, pause the video, go back and check out your notes. For example, here is my note. These are the 3 new things that I learned during this session. I got familiar with the concept of trust and how to analyze or design a trust using the method of joints. And I learned how to find a zero force member to simplify the analysis and design of the trust using the method of joints. Go ahead, practice, and let me know if you have any questions.